This is the EdExcel A Level Further Maths Paper 3, covering the Further Pure 1 FP1 module, and it's from the October 2020 series. Question number 1, we have to use L'Hopital's rule to show that the limit as x tends towards pi over 2 of e to the power of sine x minus the cosine of 3x minus e over the tangent of 2x is equal to minus 3 over 2. Well, first of all, let's see what happens as x tends towards pi over 2. Well, e to the power of sine x minus the cosine of 3x minus e, this will tend towards, well, we have here e to the power of sine of pi over 2, which is e to the power of 1, and then we've got minus the cosine of 3 pi over 2, so we subtract off 0, and then we've got minus e. So therefore, as x tends towards pi over 2, e to the sine x minus cosine of 3x minus e tends towards 0. And if we take a look at tan 2x, well, here, as x tends towards pi over 2, tan of 2x, well, that will tend towards the tangent of 2 times by pi over 2, which is tan of pi. So therefore, as x tends towards pi over 2, tan of 2x tends towards 0. And therefore, what we have is something of the form 0 over 0. So as the limit is of the form 0 over 0, we would have to apply L'Hopital's rule. So therefore, we have the limit as x tends towards pi over 2 of e to the power of sine x minus cos of 3x minus e over the tangent of 2x. Well, if we apply L'Hopital's rule, we'd have to differentiate the top, differentiate the bottom, and then evaluate the limit. So we have the limit as x tends towards pi over 2 of, well, if we differentiate the top, well, differentiating e to the sine x, we end up with cos x times by e to the sine x, and if we differentiate minus cos 3x, we end up with 3 sine 3x, and on the bottom, if we differentiate tan 2x, well, we'll end up with 2 sec squared 2x. So if we work all of this out, well, on the top we have the cosine of pi over 2 times by e to the power of the sine of pi over 2 plus 3 times by the sine of 3 pi over 2, and along the bottom we have 2 times by sec squared of 2 times by pi over 2. So on the top we have this term, which is 0, this term, which is 3 lots of -1, and on the bottom we've got 2 lots of sec squared of pi, which is -1 squared. And therefore what you can see, we do indeed end up with -3/2, and therefore the limit is equal to -3/2. Question number 2. Figure 1 shows a sketch of the vertical cross-section of the entrance to a tunnel. The width at the base of the tunnel entrance is 2 meters, and its maximum height is 3 meters. The shape of the cross-section can be modelled by the curve with equation y equals f of x, where f of x is equal to 3 lots of the cosine of pi/2 times x squared, where x is in between -1 and 1. A wooden door of uniform thickness 85 mm is to be made to seal the tunnel entrance, and we have to use Simpson's rule with 6 intervals to estimate the volume of wood required for this door, giving your answer in meters cubed to 4 significant figures. Well, over here we can use integration to find out the area of this cross section. Of course, we'd have to integrate f of x in between -1 and 1, and then we can multiply that area by 85 mm to find the volume of wood required. And for us to find out the integral of f of x between -1 and 1, as we were told in the question, we'd have to use Simpson's rule. And as we are going from -1 to 1 with 6 intervals, well, we'd start off at -1 and we'd add on step lengths of 1/3 until we get to 1, and we find out the corresponding y values, and we'll work from there. So we have our x values. We start off with -1, and then if we add on 1/3, well, here next value is -2/3, then we have -1/3, and then we have 0, 1/3, 2/3, and then 1. So here we have 6 intervals. And what we can now do is substitute into here to find the corresponding y values. So we have 3 times by the cosine of pi/2 times x squared. So here we begin with -1 squared. So it turns out here we get 0. For the next value, we have -2/3 to substitute in. So it turns out here we get 2.2981, etc. Now let's store this into A. For the next value, we have to change this to a -1/3. So it turns out here we get 2.9544, etc. Let's store this into B, and then when we're at 0, of course, we'd have 3 lots of the cosine of 0, which is just 3. Now here, for the other values, well, for x squared, if we have -1 all squared, that's the same as 1 squared. So through symmetry, this value will be 0, and -2/3 all squared is the same as 2/3 all squared. So this value here is the same as this value. So we've got 2.2981, etc. And -1/3 all squared is the same as 1/3 all squared. So this value is the same as this value. So we've got 2.9544, etc. So how does this help us? Well, for us to apply the Simpson's rule, let's first of all label these different y values. We start off with y0, then we've got y1, y2, y3, y4, y5, and y6. So therefore, applying the Simpson's rule, what we'd have then is the integral from -1 to 1 of 3 times by cosine of pi over 2 times x squared. This is approximately equal to, well, we've got a third multiplied by h, and h over here is 1/3. Of course, from one value to the next value, we keep adding on 1/3. And then we multiply this by the following. We have the first y value plus the final y value. So we've got 0 plus 0. And then we add on 4 lots of the odd values. So we've got y1, which is 2.2981, etc., plus y3, which is 3, plus y5, which is 2.2981, etc. And then we've got 2 lots of the evens, so we've got 2 lots of 2.9544, etc., plus y4, which is 2.9544, etc. So if we work all of this out, well, we've got over here, if we substitute everything in to this curly bracket first, we've got 4 lots of that value here, which I said was a, plus 3 plus a, plus 2 lots of this value, which I said was b, plus another b. And then we multiply this by a 9th, which is the same as dividing by 9. So it turns out here we get 4.689, etc. And therefore, for the volume, well, this will equal 85 over 1,000, because we need to convert the millimeters to meters, multiplied by 4.689, etc. So if we multiply this by 85 over 1,000, it turns out here to 4 significant figures. We get 0.3986 meters cubed. So this is rounded to 4 significant figures. Question number 3. The points A, B and C with position vectors 3i minus 2j plus k, I, 4j plus 5k, and minus 2i plus 3j plus 3k respectively lie on the plane pi. And for part A, we have to find AB cross with AC. Well, before we do anything else, let us find out what the vector AB is. AB, that's equal to the vector B, which is I plus 4j plus 5k minus vector A, which is 3i minus 2j plus k. So if we work this out, it turns out we get minus 2i plus 6j plus 4k. And if we work out what the vector AC is, well, we've got the vector OC, which is minus 2i plus 3j plus 3k minus the vector OA, so we subtract off this, and in doing so you will find AC to equal minus 8i, rather you'd find AC to equal minus 5i plus 5j plus 2k. And therefore, if we find out what AB cross AC is, well, here we'd have to cross this vector here so this vector here with this vector here. And if we do that, well, what we can do is simply use our calculator to do this. So on your calculator, if we go to the vector submenu, define this first vector with components minus 2, 6, and 4, and the other vector with components minus 5, 5, and 2, crossing them together, what we end up with is minus 8i minus 16j plus 20k. So we end up with minus 8i minus 16j plus 20k. For part B, we have to find an equation for pi in the form r dot with n equals p. Well, first of all, we need to recognize that the vector n, the normal vector, is the result of crossing two vectors which lie on the plane. And of course, the normal vector will be given by this result over here. And what we can also do is find out the value of p. We can find out the value of p by dot producting the vector A with the normal vector. So we've got the vector A, which is this vector here, and then we will dot this with the normal vector as we see here. So if we find out the dot product of these vectors, we have 3 times by minus 8, so let's just work all of this out. We've got 3 times by minus 8 plus minus 2 times minus 16 plus 1 times 20, it turns out here we get 28. So we end up with 28. And therefore, for the plane pi, we have r dot with n, so we dot r with this normal vector. The result of this is equal to 28. Now for part C, the point D has position vector 8i plus 7j plus 5k, and we have to determine the volume of the tetrahedron ABCD. Well, for part C, it will be a good idea to first of all sketch out this tetrahedron. So if we sketch out our tetrahedron, we have something looking like this. So this is the tetrahedron that we have. And let's just show the other line over here. So we've got the vector A, the vector B, and the vector C, and then we've got some point D over here. Well, we've just worked out the vector AB, and we've also worked out the vector AC. What we also need to do is work out the vector AD. So if we work out the vector AD, this is equal to the vector OD, which is this vector here, which is 8i plus 7j plus 5k and we subtract off the vector A, which is this vector here. So if we find the result of these, well, what we'll end up with is 5i plus 9j plus 4k. And therefore, to find the volume is equal to 1/6 multiply the modulus of AD dot product with AB cross AC. We have the triple scalar product here. So what we will have then is 1/6 lots of the modulus of, well, AD, that's this over here, and then we dot this with AB cross AC, and AB cross AC, that's this over here. So here is AB cross with AC. So now what we will do is find out the dot product of those before we do anything else. So we've got 1/6 lots of, well, here we have 5 times by minus 8 plus 9 times by minus 16 plus 4 times by 20. So it turns out here we get minus 104. So we've got a 6th lots of the mod of minus 104. And therefore, if we work this out, it turns out what we end up with is 52/3 units cubed. Question number 4. We're given that f of x is equal to x to the power of 4 times by the sine of 2x, and we have to use Leibniz theorem to show that the coefficient of x minus pi to the power of 8 in the Taylor series expansion of f of x about pi is a pi plus b pi cubed over 315, where a and b are integers to be determined, and the Taylor series expansion of f of x about x equals k is given by this result here. So before we do anything else, it might be a good idea to work out what u and v are. U, that will equal x to the power of 4, and v, that's equal to the sine of 2x. And now if we work out the first derivative of u, that's equal to 4x cubed, and the first derivative of v, that's equal to 2 multiplied by the cosine of 2x. If we work out the second derivative of u, this will equal 12x squared, and the second derivative of v, this will equal minus 4 times by the sine of 2x. The third derivative, that's equal to 24x, so that's the third derivative of u, and the third derivative of v, well, that will be minus 8 times by the cosine of 2x. The fourth derivative of u, that's equal to 24, and the fourth derivative of v, that's equal to 16 multiplied by the sine of 2x. And the fifth derivative of u, that's equal to 0, and the fifth derivative of v, that's equal to 32 times by the cosine of 2x. And in general, u, the nth derivative of u, is equal to 0 for n being greater than 4. So if we continue differentiating, we'd always get 0. And that's because of the fifth derivative being 0. Differentiating a constant gets us 0. So if we continue with v and its derivatives, the sixth derivative of v, that's equal to minus 64 times by the sine of 2x. The seventh derivative of v, that's equal to minus 128 times by the cosine of 2x. And the eighth derivative of v, that's equal to 256 times by the sine of 2x. So having worked out all these derivatives, what we can now do is apply Leibniz theorem. So here is Leibniz theorem. The nth derivative is equal to the sum of n choose k dku over dxk lots of dn minus kv over dx n minus k, and of course we take the sum from k equals 0 to k equals n, and because we're working out the eighth derivative here for us to apply the Taylor series about pi to obtain the coefficient of x minus pi to the power of 8? Well, because of that, n will equal 8. So, therefore, the 8th derivative of f, well, we start off with 8 choose 0. So we've got 8 choose 0, and then we've got the function u multiplied by v and its 8th derivative. So we multiply u by the 8th derivative of v. And then we have 8 choose 1, the first derivative of u, multiplied by the 7th derivative of v. And then we have 8 choose 2 times the second derivative of u times by the 6th derivative of v. And then we have 8 choose 3 times the third derivative of u times by the 5th derivative of v. And then we have 8 choose 4 times by the 4th derivative of u times by the 4th derivative of v. And then we have 8 choose 5 times by the 5th derivative of u multiplied by the 3rd derivative of v. And then we have 8 choose 6 times the 6th derivative of u times by the 2nd derivative of v. And then we have 8 choose 7 times the 7th derivative of u times by the first derivative of v. And finally, we've got 8 choose 8 times by the 8th derivative of u times by v. Now, we know already that the nth derivative of u is equal to 0 for n being greater than 4. So, as the nth derivative of u equals 0 for n being greater than 4, well, if we think about it, this, and this will all be 0. So, the 8th derivative of f, well, what we have is all these terms which we can still use. And then we've also got the term here, which we can still use, but we can't use anything beyond that, because the nth derivative is equal to 0 for n being greater than 4. So if we substitute everything in, we have 8 choose 0, and then we've got u, which is x to the 4. Okay? So we've got u, which is x choose 4. And then we've got the 8th derivative of v, which is 256 times by the sine of 2x. And then we've got 8 choose 1 times by the first derivative of u, which is 4x cubed, multiplied by the 7th derivative of v, which is minus 128 cosine of 2x. And then we have 8 choose 2 times by the second derivative of u, which is 12 x squared, times by the 6th derivative of v, which is minus 64 sine 2x. And then we've got 8 choose 3 multiplied by the third derivative of u, which is 24x, times by the 5th derivative of v, which is 32, times by the cosine of 2x. And then we have 8 choose 4 multiplied by the 4th derivative of u, which is 24, multiplied by the 4th derivative of v, which is 16, times by the sine of 2x. So now we need to tidy all of this up even further. And of course we can just use our calculator to work out the coefficients. So first of all, we have 8 choose 0 multiplied by 256. So here we have 256 times by the sine of 2x. For the next one, we have 8 choose 1 times by 4 times by minus 128. So it turns out here we have, rather here we've got 256 times by x to the 4 times by sine 2x, and then we've got minus 4096 times x cubed times by cos 2x. So now we have this one over here, so we've got 8 choose 2 times by 12 x squared times by minus 64 sine 2x. So here we get a value of minus 21504, and then we've got x squared sine 2x. And then here we would have 8 choose 3 multiplied by 24 multiplied by 32. So here we get positive 43008x. times by the cosine of 2x. And then here we have 8 choose 4 multiplied by 24 multiplied by 16. So it turns out here we end up with 26880 times by the sine of 2x. So this is what the 8th derivative of f is, the result we see here. So now, if we apply Taylor series to obtain the coefficient of the x minus pi to the 8 term, well, because we are expanding about pi, what we'd need to do first is work out the 8th derivative at x equals pi. So therefore, the 8th derivative at x equals pi, well, we have 256 times by pi to the 4 times by the sine of 2 pi, and then we've got minus 4096 times by pi cubed times by the cosine of 2 pi, and then we've got minus 21504 pi squared times by the sine of 2 pi, and then we've got 43008 times by pi. I'll write this on a new line actually, multiplied by the cosine of 2 pi, and then we've got 26880 times by the sine of 2 pi. And because sine of 2 pi is equal to 0, this, and this will all disappear, and because cosine 2 pi is equal to 1, what we'd end up with is 43008 pi times by 1, because cosine of 2 pi is 1, minus 4096 times by pi cubed, lots of 1, again because cosine of 2 pi is 1. So tidying this up, we end up with 43008 pi minus 4096 pi cubed. Now, what we can do is find the coefficient of x minus pi to the 8. So therefore, if we use the Taylor series to do that, the coefficient of x minus pi to the power of 8, this will be given by the 8th derivative of f at the point x equals pi divided by 8 factorial. So now if we work all of this out, we have found out what the 8th derivative is at x equals pi, that's over here. And then we divide this by 8 factorial. Now, if you remember, in the question we want a denominator of 315, so if we actually work out what 8 factorial is, 8 factorial, that's this result here, and if I divide this by 315, well, what I'd have to do is divide the top and bottom by 128. So we've got 43008 divided by 128. So here we get 315. and 36 pi. And then we've got 4096 divided by 128. So here we get 32 pi cubed. And then we've got 8 factorial divided by 128. So just make sure we type in the correct thing. So we've got 8 factorial divided by this, so that's 315. And therefore, what we can conclude is A is equal to 336 and B is equal to minus 32. Question number 5. The ellipse E has equation x squared over 36 plus y squared over 16 equals 1. The points S and S' are the foci of E, and for part A we have to find the coordinates of S and S'. Well, if we rewrite our ellipse in a different form, you can see that we can rewrite this as x squared over 6 squared plus y squared over 4 squared equals 1. The reason we can do that is because now we can see that A is equal to 6 and B is equal to 4. And if we go to the formula book, under the conic section for an ellipse, we've got the foci given by plus minus AE 0, and the eccentricity given by b squared equals a squared lots of 1 minus e squared can be used to find the value of e, which will help us allow us to find the foci. So we've got b squared equals a squared lots of 1 minus e squared. So we've got b squared, which is 16. This is equal to a squared, which is 36 lots of 1 minus e squared. And if we solve for e, well, we have 16 over 36. And then we've got 1 minus this, which is 5 over 9. And therefore, we've got e squared equaling 5 over 9. So let's just write that down here. We've got e squared, which is equal to 5 over 9. And therefore, e is equal to plus minus, rather we'll just leave it as a positive value. We've got e equals root 5 over 3. And if we use the fact that the foci are at plus minus AE 0, we can therefore conclude that the foci would have coordinates well, we have S dash, which is negative AE, so we've got negative 6 times by root 5 over 3, which is negative 2 root 5, and then we've got 0. And also, we've got S, which would have coordinates positive 2 root 5, 0. So all we've just done here is multiplied 6 by root 5 over 3 to get 2 root 5. And we've also got the negative of that as well here. Now for part B, we have to show that for any point P on E, the triangle PSS' has constant perimeter, and we have to determine its value. Well, before we do anything else, I think it might be a good idea to sketch the ellipse. So you can see here, we've got an ellipse, and we've got the directrices as we see here. So first of all, the directrices, if we go back to the formula book, that's given by x equals plus minus a over e. So we've got over here x equals the positive of a over e, so we've got 6 over root 5 over 3. Well, what we'll do actually instead is we'll leave this as a over e, and you'll see why I'm doing that. It just makes the maths tidier. And we've also got the negative x equals negative a over e. Now, if we add on our foci, well, first of all, you can see that the ellipse crosses the x-axis at positive 6 and negative 6, positive 4 and negative 4. Okay, and if we add the foci, we have somewhere here and here, the foci, we've got 2 root 5, 0. So this is what S is, and S dash, that will be negative 2 root 5, 0. So if we suppose that the point P over here somewhere has general coordinates x, y, then the distance over here from P to the directrices, well, we can determine what that is. And we've also got the distance from P to the foci. So if we show those, we've got here the distance P S dash, and here we've got the distance PS. And of course, if we go back to the question, we're looking at the perimeter of the triangle PSS dash. So for the perimeter, this will equal P S dash plus S dash S, which is this distance, plus P S. And the reason I mentioned the distance from the point P to the directrices, well, what we know already, if we call this point here M dash, and if we call this point M, then what we know already is that PS over PM is equal to E, and also P S dash over PM is also equal to E. And from this, what we can conclude then is PS is equal to PM multiplied by E, and PS dash is equal to PM dash multiplied by E. So therefore, what we can conclude for the perimeter, so let's just actually swap these around for a second. For the perimeter given by this result here, this will equal P S dash, which is P M dash multiplied by E, plus SS dash, well, the distance from from s dash to s, that will be the difference between 2 root 5 and minus 2 root 5, which is 4 root 5. And then we add on ps, which we said is pm multiplied by e. So we have 4 root 5 plus e lots of pm dash plus pm. Now we can actually find the distance pm dash and pm. Well, over here, pm dash, the distance from here to here, as of course p moves around the ellipse, that will be x plus a over e. We're going from minus a over e to x, so therefore that distance will be x plus a over e. And pm, well, from p to m, we're going from x to a over e, so that distance will be a over e minus x. So we've got e lots of this result, and then of course don't forget we need to add on the 4 root 5. So if we tidy this up, we have 4 root 5 plus e lots of, well, here we would have x minus x, which is 0x, and then we've got a over e plus another a over e. So here we would have 2a over e. And the e's here cancel. So we have 4 root 5 plus 2a, and knowing the fact that a, if we go back, is equal to 6, we have 4 root 5 plus 2 lots of 6. Indeed, the perimeter is equal to 4 root 5 plus 12. So therefore, the perimeter is constant for any p on E. Question number 6. A physics student is studying the movement of particles in an electrical field. In one experiment, the distances in micrometers of two moving particles, A and B, from a fixed point O are modelled by dA equals mod of 5t minus 31 and dB equals the mod of 3t squared minus 25t plus 8. And t over here is the time in seconds after motion begins. And for part A, we have to use algebra to find the range of time for which particle A is further away from O than particle B is from O. Well, over here, we are solving the inequality mod of 3t squared minus 25t plus 8 being less than the mod of 5t minus 31. And what we can do before we move on to anything else is find out the critical values and then sketch a graph, and from that we can find the solution to this inequality. So first of all, we can replace the modular sign with an equal sign to help us find the critical values. So we've got the mod of 3t squared minus 25t plus 8 equaling mod of 5t minus 31. And of course here then we will end up with 3t squared minus 25t plus 8 equals plus minus 5t minus 31. Now if we deal with the positive and negative separately, well, dealing with the positive, we have 3t squared minus 25t plus 8 equals 5t minus 31. And if we rearrange, we have 3t squared minus 30t plus 39 equals 0. And if we solve this, well, let's jump onto the polynomial solver. We have 3 minus 30 and 39 to input into our calculator. So it turns out here t is equal to 5 plus minus 2 root 3. And if we deal with the negative, well, we'd have 3t squared minus 25t plus 8 equals 31 minus 5t squared, rather minus 5t. So if we rearrange here, we have 3t squared minus 20t minus 23 equals 0. And if we solve this, so we've got 3 minus 20 and minus 23 to put into our calculator. So we get two values. We end up with t equaling minus 1 and 23 over 3. So now what we can do is draw a sketch of dA and dB. So if we draw a sketch of these, well, if we think about dB before we do anything else, if we go back to our calculator, we've got 3t squared minus 25t plus 8. So it crosses the x-axis at a third and 8. It's got a minimum at 25 over 6, and that's if we don't include the mod signs. So therefore the maximum of this will be at, well, rather the minimum occurs at this point, and the minimum here is negative, and of course when we mod that, the maximum will be positive 529 over 12. So let's sketch dB first. Here you can see what dB is, and we mentioned it crosses at 1/3 and 8, and it's got a maximum over here somewhere, but we're not really interested in that. And if we sketch the mod of 5t minus 31, well, first of all, 31 divided by 5, that is 6.2. So therefore its vertex is at 6.2, it crosses at positive 31, which is over here somewhere. And then if we showed the same on the other side, we've got here dA, and here crosses at 31 rather over 5. Now if we show our critical values, well, we have 4 points over here. This point over here would correspond to the -1. This point over here would correspond to the 5 minus 2 root 3. This point over here would correspond to 23 over 3, and this point here would correspond to 5 plus 2 root 3. So therefore we've got the graph of dB and dA. And if we show where they cross the y-axis, well, this one would cross the y-axis at 8, and this would cross the y-axis at 31. So now, if we go back to the original problem, we're looking at where dB B is less than dA, and it's less than dA everywhere in between here and also in between here. So therefore, for the solutions to the inequality, we have -1, which is less than t, which is less than 5 minus 2 root 3. And what we also have is 23 over 3, which is less than t, which is less than 5 plus 2 root 3. So here are our solutions to the inequalities. Now for part B, it was recorded that the distance of particle B from O was less than the distance of particle A from O for approximately 4 seconds, and we have to use this information to assess the validity of the model. Well, let's just sketch out this graph once again for part B. Here is our graph once again, and what we're looking for is the time that B is closer to O than A. Well, over here, the time that B is closer to O than A, well, we've got this bit over here, and then we've got this bit over here. Of course, time can't be negative. So therefore, we have this time over here from the y-axis to here. So we've got 5 minus 2 root 3. And then we've got the difference between these. So then we add on 5 plus 2 root 3 minus 23 over 3. So if we work all of this out, well, we have here the minus 2 root 3 and the positive 2 root 3 cancelling. So we've got 5 plus another 5 minus 23 over 3. So here we get 7 over 3, which if we work out its decimal equivalent, we get 2.33, etc. So this is the time for which B is closer to O than A. And this over here is less than the 4 seconds that was described to us from the question here. And therefore, what we can conclude is the model does not seem appropriate. Question number 7. The points P with coordinates 9p squared, 18p, and Q with coordinates 9q squared, 18q, where P doesn't equal Q, lie on the parabola C with equation y squared equals 36x, and the line L passes through the points P and Q. And for part A, we have to show that an equation for the line L is given by P plus Q lots of y equals 2 lots of x plus 9pq. Now, before we do anything else, part A, we're given already y squared equals 36x, and if we compare this with the standard result for a parabola, where we've got y squared equals 4ax, well, 4a would equal 36, and therefore the value of a is equal to 9. And with this, of course, we can find out the focus, and we can also find out the directrix. So now what we will do is sketch the graph of y squared equals 36x. So here is the graph of y squared equals 36x, and if we have some point here, say, we'll call this point here S. Well, S, which is the focus, would have coordinates 9, 0. And if we show the equation of the directrix, well, the directrix would be over here, and it would have equation x equals -9. And what we have already is the point P. We'll say point P is here somewhere, and it's got coordinates 9 p squared, 18 p, and then we've got the point over here somewhere. We'll call this point here Q, and it has coordinates 9q squared, 18q. And what we need to do is find out the equation that connects P to Q. So we will be finding this equation over here. So this is what we need to do. So here is the line L. Now, of course, to find L, what we need first of all is the gradient of PQ. So therefore, for the gradient of PQ, we've got the change in y's, so we've got 18q, take away 18p, over the change in x, which is 9q squared minus 9p squared. And on the top, if we factorize out the 18, we've got 18 lots of q minus p. And on the bottom, we have 9 lots of q squared minus p squared. On the bottom, we can factorize that as a difference of 2 squares, and also we can recognize that 18 divided by 9 is 2. So here we have q plus p, lots of q minus p on the bottom, and on the top we have 2 lots of q minus p, and the q minus p's cancel on the top and bottom, leaving us with p plus q on the bottom, and on the top we've got 2. So that's the gradient of PQ. And using y minus y1 equals m lots of x minus x1, what we can do is find the equation of line L. So for line L, we've got y minus 18p. This is equal to gradient, which is 2 over p plus q, lots of x minus 9p squared. And now we just need to tidy all of this up to show the result as we see here. So first of all, let's multiply both sides by p plus q. So we have p plus q lots of y minus 18p lots of p plus q, and then here we'd have 2 lots of, and if I expand into the brackets, x, and then we've got 2 lots of minus 9p squared, so that will be minus 18p squared. So now we need to take this result over to the right hand side. So we've got p plus q y equals 2x plus 18p lots of p plus q plus, rather, minus 18 p squared. So we've got p plus q lots of y equals 2x, and if we factorize out the 18p from both terms, we have positive 18p lots of p plus q minus p. And then if we recognize that p minus p is equal to 0, what we would have then is p plus q lots of y equals 2x plus 18 p q. And if we go back to what we want to show, a 2 has been factorized out, so therefore we can conclude that L has the equation p plus q lots of y equals 2 lots of x plus 9p q. Now for part B, the normal to C at P and the normal to C at Q meet at the point A, and we have to show that the coordinates of A is given by this result, 9 lots of p squared plus q squared plus pq plus 2 in the x direction and minus 9pq lots of p plus q in the y direction. Well, if we go back to our diagram and amend it, well, over here somewhere we would have the tangent at the point P, okay? And over here somewhere we would have the tangent at the point Q. And now what we need to do is find the normals of those. So, well, let's just label these. Here we've got the tangent at the point Q, and here we've got the tangent at the point P. And now what we can do is find the perpendiculars of those. So the normal to P, that will be what's here. So here we've got the normal to P, we'll write that down later, and then here we've got the normal to Q, which is shown over here. So we've got here the normal to Q, and here we've got the normal to P, which we'll write, we'll continue this line over here somewhere. So here we have the normal to P, and of course they meet at the point A. So here we have A. Now for us to find where they intersect, well, I need to find out the equation of the normal to P and Q, and for me to do that I need to find the gradient of the tangent at both P and Q, and use the fact that the normal and the tangent are perpendicular to each other to find the gradient of the normals, and then with that we can find the equation of the normals. So for part B we have y squared, which is equal to 36x, and if we differentiate implicitly we have 2y lots of dy over dx equals 36, from which we can see dy over dx, this is equal to 36 over 2y, which is the same as 18 over y. So all we now need to do is substitute in the y coordinate of both p and q. So at the point P, if we substitute in, we have dy over dx. This is equal to 18 over the y coordinate of P, which you'd remember is 18p. So here we get we get 1 over p, which is the gradient of the tangent. So therefore, the gradient of the normal at P will equal negative P. And therefore, for the equation of the normal, we would have y minus 18p equals minus p lots of x minus 9p squared. And if we expand into the bracket, we have y minus 18p equals minus px plus 9p squared. And if we tidy this up, what we can do is find out the equation of the normal to p. So therefore, for the equation of the normal to p, we would have y equals minus px plus 18p plus 9p cubed. Of course, here we'd have cubed. And we can do a similar thing with the point Q. So at the point Q, we'd have exactly the same thing here. We have dy over dx, which is equal to 18 over 18q. So this, of course, is 1 over q, which would represent the gradient of the tangent at q. So the gradient of the normal at q, that's equal to minus q. So we have y minus 18q equals minus q lots of x minus 9q squared. And if I expand in, we've got 9 minus 18q equals minus qx plus 9q cubed, from which we can see the normal as equation y equals minus qx plus 18q plus 9q cubed. So this over here is the equation of the normal at q, and here we've got the equation of the normal at p. So now what we can do is set those equal to each other to find out the coordinates of A. So what we'll do first of all is write those normal equations down. We have here y equals minus qx plus 18q plus 9q cubed, and the normal to p, we've got y equals minus px plus 18p plus 9p cubed. And for the line L over here, we have p plus q lots of y equals 2 lots of x plus 9p q. So what we will now do is set those equal to each other to find out what the x coordinate of A is, and then we can find out the corresponding y coordinate. So we've got minus px plus 18p plus 9p cubed equals minus qx plus 18q plus 9q cubed. So if we gather everything involving an x on one side and everything that's not an x on the other side, we have px minus qx equals Well, we have 18p minus 18q plus 9p cubed minus 9q cubed, and if we attempt to factorize, we have p lots of we have x lots of p minus q equals 18 lots of p minus q plus 9 lots of p cubed minus q cubed. So now what we can do is recognize that p cubed plus minus q cubed can be factorized. So if we factorize that, what we'd have is p squared plus pq plus q squared lots of p minus q. And of course, over here, all we're saying is p cubed minus q cubed is p squared plus pq plus q squared lots of p minus q. So what we can now do is factorize out a p minus q from every term. So we've got x lots of p minus q equals p minus q lots of, well, we'd have 18 plus, and if I expand the 9 into this first bracket, we'd have 9p squared plus 9pq plus 9q squared. So the p minus q's cancel, and therefore would be left with x equals this result over here. So now what we're going to do is factorize out a 2 from every term. Rather, we're going to factorize out a 9 from every term. So therefore, xa will equal 9 lots of p squared plus q squared plus pq plus 2. So that's the x coordinate of A. And now what we can do is find the corresponding y coordinate by substituting into either this or this. So if we find out the corresponding y coordinate, we have over here minus px. So we've got minus, if we go back over here, we've got minus px, so we've got minus p times by 9, so that's minus 9p, and then we've got this bit over here as well. Okay, and then we've got the other terms as well, which we had. We've got the plus 18p plus 9p cubed. So let's add those on. We've got plus 18p plus 9p cubed. So now what we can do is expand into the bracket. So we have y equals minus 9p cubed minus 9p q squared minus 9p squared q minus 18p plus 18p plus 9p cubed. And you can see which terms cancel, and therefore y will equal minus 9p squared q minus 9q squared, rather minus 9p q squared. And if we factorize out a minus 9pq, we can therefore conclude that the y coordinate of A will be given by minus 9pq lots of p plus q. So therefore, for the coordinates of A, we have this for the x coordinate, and then for the y coordinate we have this over here. So therefore, this is the coordinates of A. And what we'll do as well, we'll add this to the diagram just to make things a bit clearer. So we've got A with coordinates 9 lots of p squared plus q squared plus pq plus 2, and we've got minus 9 pq lots of p plus q. And now for part C, given that the points P and Q vary such that L will always pass it through the point 12 and then 0, we have to find in the form y squared equals f of x an equation for the locus of A giving f of x in its simplest form. Well, what we're saying is this line over here, L, always passes through 12, 0. So let's see how we can use that. For part C, if we consider this point 12, 0, and if we consider our line for L, which was over here, we would have P plus Q lots of 0 equals 2 lots of 12 plus 9pq. So therefore we have 0 equals 12 plus 9pq, from which we can conclude pq equals minus 4 over 3. And the reason I want to work this out is because you can see here we've got a pq and here we've got a pq. It just makes things a little easier. So therefore what we can do is find out the coordinates of A. So for the coordinates of A, which is what we have here, so just copy paste this, what we will now do is replace the PQ with minus 4/3. So all we've just done is replace PQ with minus 4/3, and in doing so we can therefore conclude that A now has coordinates 9 lots of p squared plus q squared plus 2/3, and then we've got here 12 lots of p plus q. And what we need to do is find the locus of A as P and Q move around, but of course the line L will always remain fixed. So with that, what we will do is we will let A have coordinates x, y. And if we do that, well, what you can see is x is equal to this result here, and also y will equal 12 lots of p plus q. So how does this help us? Well, first of all, here we've got a p squared plus q squared. So let's just make a note of some rearranging. So first of all, note that, well, we know that p plus q all squared is equal to p squared plus 2pq plus q squared. So we've got p squared plus q squared equaling p plus q squared minus 2pq. And recognizing that pq is equal to minus 4/3, we have p squared plus q squared equals p plus q all squared minus 2 lots of minus 4 over 3. And therefore p squared plus q squared that's equal to p plus q all squared plus a over 3. And from here, we can actually find out what p plus q is. So, if we rearrange that, as p plus q is equal to y over 12, what we'd therefore have is p squared plus q squared equaling y over 12 all squared plus a over 3. So this over here is what p squared plus q squared is, and what we can now do is substitute that into here. So therefore, x, which is equal to 9 lots of, well, here we've got p squared plus q squared, which we've just said is y over 12 all squared plus a over 3. So that's what p squared plus q squared is, and then we've got the extra 2/3. So, how does this help us? Well, what we've got then is x equaling 9 lots of, well, here we've got y over 12 all squared, and then we've got 8 over 3 plus 2 over 3, so that's 10 over 3. And now if we multiply the 9 into the bracket, we have x equals, well, here we'd have 9 y squared over 144, and then we've got 9 times by 10 over 3, which is just 30. And if we multiply through by 144, you can see that 9y squared is equal to 144x minus, well, 144 times 30, that's 4320. And now if we divide through by 9, y squared, that will equal 16x minus 480, and if I factorize out a 16, we can therefore conclude y squared is equal to 16 lots of x minus 30. This is in its simplest. Question number 8. Given that f of x is equal to 3 over 13 plus 6 sin x minus 5 cos x, and for part A, we have to show that f of x can be written in the form 3 lots of 1 plus t squared over 2 lots of 3t plus 1 all squared plus 6. So for part A, if t is equal to tan of x upon 2, then sin x, that's equal to 2t over 1 plus t squared. Then cos x, that will equal 1 minus t squared over 1 plus t squared, and tan x, that's equal to 2t over 1 minus t squared. So now what we can do is rewrite f of x, this time replacing sin x and cos x with the appropriate t formulae. So we know already f of x is equal to the following. We have 3 over 13 plus 6 sin x minus 5 cos x. So if we replace as necessary, we have 3 over 13 plus 6 lots of sine x, which is 2t over 1 plus t squared. And then we have minus 5 lots of cos x, and cos x is the same as 1 minus t squared over 1 plus t squared. So this here is what f of x is equal to. So let's just tidy this up and just write it slightly more neatly. So here is what f of x is. Now what we can do is write the 13 such that we'd have a denominator of 1 plus t squared. So if we do that, well, everything else will remain the same, apart from the 13, which we're rewriting as 13 lots of 1 plus t squared over 1 plus t squared. Okay, so then everything else over here is the same. Okay, so let's just write this out neatly. So now that we've got this common denominator of 1 plus t squared, what we can now do is multiply both the top and bottom by 1 plus t squared. And if we do that, well, on the bottom we'd have 13 lots of 1 plus t squared plus 6 lots of 2t minus 5 lots of 1 minus t squared. And on the top we have 3 lots of 1 plus t squared. So now if we expand and simplify, well, along the bottom we'd have 13 plus 13t squared plus 12t minus 5 plus 5t squared, and on the top we'd have 3, well, rather we can leave the top as it is, and the reason for that is if you pay attention to the show that we have here a 1 plus t squared in a bracket, so we'll leave the top as it is. So if we continue to tidy all of this up, well, on the bottom we'd have 13t squared plus 5t squared, that will be 18t squared, and then we've got the 12t, and then we have 13 minus 5, which is positive 8. And then here on the top we have 3 lots of 1 plus t squared. Okay, so to write this in the required form, well, what we'll do is, if you notice over here we have 2 lots of 3t plus 1 all squared, and if I square 3t we'd end up with 9t squared, and if I multiply that by 2 I get the 18t squared. So we can adapt what we have here so it can look similar to what we want to show. So if I rewrite the bottom, we can rewrite the bottom as 2 lots of 9t squared plus 6t plus 1 plus another 6. And the reason for that, well, here 2 lots of 9t squared gives the 18t squared, 2 lots of 6t gives the 12t, and then we've got 2 times by 1, which is 2, plus the 6, that gives the 8. And this square bracket, you'd find, is what this is, the 3t plus 1 all squared. So this is what we have here, and on the top, let's keep that the same. we have 3 lots of 1 plus t squared. So it turns out here f of x is equal to 3 lots of 1 plus t squared over 2 lots of 3t plus 1 all squared plus 6. So that is what f of x is equal to. And now for part B, hence solve for x being in between 0 and 2 pi, the equation f of x equals 3 over 7, giving it answers to do the decimal places as appropriate. So for part B, we have f of x, which we know is this result here. Well, let's just write it out in full. We have f of x, which is this over here, and what we're doing is solving this equation equal to 3 over 7. And if we use what we found in part A, then here we've got f of x, which we re-expressed with the t formulae. Of course, this will equal 3 over 7. So, if we rewrite this result here using the result we found here, that makes things a bit easier. So, we have over here 3 lots of 1 plus t squared over 18 t squared plus 12t plus 8, which is this here, and this will equal 3 over 7. And now if we cross multiply, we have 7 lots of 3 lots of 1 plus t squared equals 3 multiplied by 18 t squared plus 12t plus 8. So now if we expand on both sides, well, here we've got 21 times by 1 plus t squared, so that will be 21 plus 21 t squared, and here we've got 3 times by 18, which is 54, so we've got 54 t squared, 3 times by 12, that's 36, so we add on 36t, and then 3 times by 8, that will be 24. And if we take everything over to one side, you'd find we get 11 t squared plus 12t plus 1 equals 0, from which you can see 11t plus 1 lots of t plus 1 equals 0, and if we solve for t, t is either equal to minus 1 or minus 1 over 11. Now over here, we know already t is equal to tan of x upon 2. So as t is equal to tan of x upon 2, well, what we're solving then is tan x, rather tan of x upon 2 equals minus 1 and minus 1 over 11. And our original domain we have, we're solving in between 0 and 2 pi. Now, if we change the domain, what we'd have is 0, which is less than x over 2, which is less than pi. So, we have here x upon 2. This is equal to, well, if we work out the inverse tangent of minus 1, we get minus 1 over 4 pi, and then if I add on pi to make sure we're in the correct interval, we get 3 pi over 4. And if I do the inverse tan of minus 1 over 11, we get a value of minus 0.09 etc. and then if I add pi to this, we get 3.050 etc. So we need to find out what x is. So all we have to do is multiply through by 2 and give our answers where necessary to 2 decimal places. So 2 times by 3 pi over 4, that will be 3 pi over 2. And if I multiply this by 2, we end up with 6.10 given to 2 decimal places. So these are the values of x in our required domain. For part C, we have to use the result of part A to show that the integral of f of x with respect to x in between pi over 3 and 4 pi over 3 is equal to k lots of the arctangent of root 3 minus 9 over 3 minus the arctangent of root 3 plus 3 over 3 plus pi. And k is a constant to be determined. Well, clearly, what we'd be integrating here is 3 over 13 plus 6 sin x minus 5 cos x. So we will be integrating this over here. Okay? So we have the integral from pi over 3 to 4 pi over 3 of this here with respect to x. Now clearly we used the t formulae. So with the t formulae, if t is equal to tan of x upon 2, well, the first thing to notice here, if t is equal to tan of x upon 2, then what we should spot, and it's quite difficult to spot this, x cannot equal pi. Otherwise, we'd have an undefined value when we have tan of pi upon 2. So hopefully this makes sense. And therefore, as a result of that, we'd have to rewrite this result over here as the following. We will now be integrating this result, but we'd have to split this integral up into 2 separate parts. We'd have to split this up from pi over 3 to pi. Okay. And then let's just copy and paste this. And then we add on the integral from, so let's just paste that again. We have this over here, plus the integral from pi to 4 pi over 3 of that. And spotting this is actually quite difficult, okay? So let's just bunch all of this together. We have dx here and dx here. Just move all this closer. So this is what we're working out. And it's quite difficult to spot that result that I've just mentioned, of how if x doesn't equal pi, we'd have to split this up into 2 separate parts. Now, what we'll do is we'll redefine our limits in terms of t. So, if we do that, well, when x is equal to pi over 3, using what we have here, we have the t equaling the tangent of pi upon 3 over 2. So we've got the tangent of pi over 6, which you'd find to equal root 3 over 3. And similarly, well, here we'll do it in a different colour. When x is equal to pi, we'd have t equaling the tangent of pi upon 2, which is equal to infinity. And when x is equal to 4 pi over 3, t is equal to the tangent of 4 pi over 3 over 2. So we've got the tangent of 4 pi over 6, which is 2 pi over 3. So it turns out here, if we work this out, we've got the tangent of 2 pi over 3, which is minus root 3. So these are our new limits in terms of t. And also, if t is equal to the tangent of x upon 2, well then dx is equal to 2 over 1 plus t squared dt. So now what we'd have to do is transform the integrals to t. So let's just write that down. We will now transform this into t. So therefore, what we have is, well, if we use the result in part A, this result over here we have, in terms of t, we got this over here. So let's just copy and paste this. So we've got the integral from, well, here before we had pi over 3, but when we transformed that to t, we got root 3 over 3. So here we've got root 3 over 3. Let's just move this slightly. And then for the upper limit, well, we'll go off to positive infinity. And don't forget, we need to multiply this by 2 over 1 plus t squared dt. Okay, so just be a bit careful with that. So that's that one sorted. So now we need to sort this one out. Well, here we add on this thing over here, and we need to redefine our limits. So if we do that, we've got the integral from pi to 4 pi over 3. Well, 4 pi over 3, that'll be, in terms of t, minus root 3. So here we'd have minus root 3. But because our upper limit is minus root 3, our lower limit will be negative infinity. So hopefully that makes sense why it's minus infinity, because we can't have our limits going from positive infinity to negative root 3, when here we're going from root 3 over 3 to infinity, so we have to ensure that this one here is negative. Now what we'll do is we'll consider this integrand, so let's consider the integral of 3 lots of 1 plus t squared over 2 lots of 3t plus 1 all squared plus 6 multiplied by 2 over 1 plus t squared dt. Let's attempt to tidy this up as much as we can. Well, what you'd find here is the 1 plus t squared cancels with this 1 plus t squared, and then this 2 cancels with this 2, and then it cancels with this over here 3 times. What this will be equivalent to is the integral of 3 over 3t plus 1 all squared plus 3 dt, which I'm going to rewrite as the integral of, well, I'm going to rewrite this as actually 3 lots of the integral of 1 over 3t plus 1 all squared plus root 3 squared. And the reason for that will become apparent. And don't forget we've got here dt. So now if we attempt to work this out, well, we'd have here 3 lots of, now 1 over 3t plus 1 all squared plus root 3 squared dt. If we go to the formula book, then under the integration section, what we have is we're integrating something of the form 1 over a squared plus x squared, and here a is equal to root 3. So therefore, the result of integrating this is 1 over a times by the arctangent of x upon a. But we don't have an x. Instead of us having an x, we have a 3t plus 1. So the result of this is, well, clearly a here is root 3. So here we have 3 lots of 1 over a, which is 1 over root 3, times by the arc tangent of, well, instead of us having an x, we've got a 3t plus 1, and we divide this by a, which we said is root 3. And don't forget we've got a plus c. So how does this help us? Well, what we can now do is continue to work this out. So in other words, we have the integral here, which is equal to, well, for the first one, we'd have 3 over root 3 times by the arctangent of 3t plus 1 over root 3, and we're working this out in between, if we go back, root 3 over 3 and infinity. So we've got root 3 over 3 to infinity, and then we add on, well, here we've got 3 over root 3 times by the arctangent of 3t plus 1 over root 3 from minus infinity up to minus root 3. So hopefully everything I've said so far makes sense. I've worked this out over here to be this here, and then with our limits we're working this out. So now we need to work all of this out. Well, if we got a limit of infinity and minus infinity, well, we need to change that. So this will equal the limit as, say, lambda tends towards infinity of 3 over root 3 times by the arctangent of 3t plus 1 over root 3, and then we're evaluating this from root 3 over 3 up to lambda, and then here we have the limit as, say, mu tends towards infinity of 3 over root 3 times by the arctangent of 3t plus 1 over root 3. And here we'd have minus mu, and here we'd have minus root 3. So what you need to recognize in this question is, therefore, we had an improper integral. And that's because t is undefined when x is equal to pi. Hence we had an improper integral. So now all we have to do is work all of this out. So if we work this out, well, here what we have is the limit as lambda tends towards infinity of 3 over root 3 times by the arctangent of 3 lambda plus 1 over root 3, and then we subtract off lower limit, which is simply 3 over root 3 times by the arctangent of 3 times by root 3 over 3 plus 1 divided by root 3. So that was this one here. And then we have the upper limit, take away the lower limit. So here we add on 3 over root 3 times by the arctangent of 3 times by negative root 3 plus 1 over root 3 minus the limit as mu tends towards infinity of, over here, 3 over root 3 times by the arctangent of, well, here we'd have, if we substitute in minus mu, we'd have minus 3 mu plus 1 over root 3. So now we need to work all of this out. Okay? So there's a lot going on over here so far. So make sure you do follow what I've done. But if we work all of this out, well, here, as lambda tends towards infinity, we have the arctangent of infinity, which is just pi over 2. So we've got here 3 over root 3 times by pi over 2. So that's this term here. And then we subtract off 3 over root 3 times by the arctangent of, well, if I substitute all of this into my calculator, what's inside the bracket, we've got 3 root 3, because 3 times by root 3 over 3 is just root 3. And then I've got plus 1, and then on the bottom I've got root 3. So here we end up with 9 plus root 3 over 3. So let's just write that down. We've got 9 plus root 3 over 3. And then we add on 3 over root 3, lots of the arctangent of, well, here, if we work that out on the top, we've got minus 3 root 3 plus 1 over root 3, which is minus 9 plus root 3 over 3, which I'm going to rewrite as root 3 minus 9 over 3. And then here we've got minus, well, as mu tends towards infinity, here we're going to have negative infinity inside the bracket. So we've got the arctangent of negative infinity, which is just minus pi over 2. So we've got 3 over root 3 times by negative pi over 2. So do be careful over here. Of course, here we've got negative infinity inside the bracket, so arctangent of negative infinity is minus pi over 2, and we're multiplying that by negative 3 over root 3. So if we tidy all of this up even further, we've got 3 over root 3 times by pi over 2, plus another, because here we've got minus and a minus which give a plus. So we add on 3 over root 3 times by pi over 2, and then we add on 3 over root 3 times by the arctangent of root 3 minus 9 over 3 minus 3 over root 3, lots of the arctangent of 9 plus root 3 over 3. So if we go back to our show that, we have something looking like the result which we want to show, and what's happened is k has been factored out, and you can see here the common factor is 3 over root 3. So therefore, if we simplify all this, the integral from pi over 3 to 4 pi over 3 of the 13 plus 6 sine x minus 5 cos x. So this result over here, if we factorize out the 3 over root 3, and then open up a big curly bracket. Well, here we've got pi over 2 plus another pi over 2, so that's just pi. And then we've got here the arctangent of root 3 minus 9 over 3. And then here we've got minus arctangent of 9 plus root 3 over 3. And then we add on pi. So this is the result which we wanted to show. And therefore, if we were to state the value of k, k would simply be 3 over root 3. So that's the end of this particular part of the question. It's quite difficult to spot what was going on, but just to summarize, we first of all needed to transform the integral here in terms of t. We also needed to recognize that we'd have an asymptote when x is equal to pi if t is equal to tan of x upon 2. And because of that, we had to split this integral up into two separate parts with our limits. And then once we transform to t, well, we change the x limits into t limits. And then, of course, when x is equal to pi, we'd have t being infinity. And then we found out what dx was, and then we transformed this integral to t limits, as we saw here. We worked the bit in green out to simplify the problem a bit, and then we worked out the improper integral, and the result was as we see here. So quite a difficult question, but hopefully you've understood what's going on.